Hey everybody, welcome back. Just getting things underway, getting things started here. Hope you guys are doing really good, staying healthy and safe. It's Tuesday, April 28th, and I'm here to deliver for you guys the lecture that you need today on chapter 12, all about science. So that's the goal. We're going to cover that material today and finish it up, and then you have your quiz on chapter 12 this Thursday. So obviously, want to pay attention, take good, clear notes, make sure you read that chapter, and then you'll be set to go for hopefully a good, successful quiz this next class period. So I'm just getting my things in order here. Find a better one than all these. Gotta make sure the markers are good. Hey Twan, nice to see you. Hey Kobe, or sorry, Connor. I mean, you know, your username, but anyways. How's it going, Connor? Good to see you. I'll be right back. I'm gonna check on another marker. Couple more of these. Let's see. That's not much better. That looks pretty good. Okay. Hello, everybody. Anybody that's watching, attending right now, feel free to just say hi. It's always good to see who's out there, but I guess it's actually a small group for now. I just have a few of you. I can see the numbers. So most people kind of just arrive right at the last minute or right after class starts. At least this is what I've noticed in this new format that we've all been working with. But yes, a couple more minutes, 5 minutes, then we'll go over these notes. I don't know if we'll take the full class period to deliver the remaining notes on chapter 12, but we'll just go as far as it needs to go, and then we'll see. Hey, Madison, Maddie, how are you? Good to see you there too. Okay. You guys have been able to, enjoy yourselves and be productive with your schoolwork and everything during this little bit of quarantine lockdown time. I've been going back to the basics, reading, playing some video games, watching lots of different shows and stuff that I'm trying to catch up on, a lot of streaming. Trying to get out and exercise. I do a little bit of running in a socially distanced, responsible way. Establishing new routines. Hopefully we'll be back to normal later in the year, but either way, we're good to go. We'll be fine. But welcome back, everyone. Good morning. Just hang in there in a few more minutes and we'll be ready to roll. Hey there, how's it going? Okay. All right, good. Just a few more moments. And, as usual, kind of always good to remember that you should always feel free to ask any questions, any comments. If there's anything on your mind having to do with this class or anything else, I'm always here, happy to help. And sometimes during the live stream, it's a good time to get those questions in. So don't hesitate if there's ever anything I could answer for you or anything you need, just let me know. And I'll respond. It's good for everybody, I think, have a little interaction. So you'll let me know if you have any thoughts, questions, comments, or anything else. But to all you guys showing up, welcome. Good morning. Glad you guys are here, and I appreciate your attendance. Just another minute or so, and then we'll just start to go over these notes for today. Okay, guys, well, just a few seconds left until it's 11:10, but might as well just get things started. So good morning to everybody. Welcome back. Welcome back to Intro to Critical Reasoning and Writing, Philosophy A150. Hey, Sam. Hope you're doing well, too. This is our Tuesday meeting for April 28th, and this is the 11:10 to 12:35 crew. Welcome back, guys. What we're doing is going over the second half of Chapter 12. So, we're right on schedule with our class overall. If you just look at the syllabus, you'll see that we're following those dates. Hey, Carmen. And that means that this week, next class, Thursday, you guys have your last quiz. That quiz is on just on Chapter 12, just on science. So these are important lectures to get you prepared for that quiz. I'm basically going to ask you, like I have on the previous quizzes, a number of like 16 or 17 questions about topics, terms, vocabulary, concepts that come from this Chapter 12. And that's what we will do next class. So there's not a lecture next class, as we've seen in the past when there's a quiz day. It's just for you guys to take the quiz and return your answers to me within the designated window of time. So we're going to do that again Thursday. I'm going to distribute by Canvas the quiz form right around class time, and you guys will have until the end of class time, basically 12:35 p.m., to return back to me your completed answers. Just remember about when you send it back to me that there have been multiple different cases of delivery and submission issues when a student hits reply to the Canvas posting, which includes the attached file. So don't do that. Just I would request that you create a new email, compose message, and then manually type in my email address, rvulich@occ.cccd.edu, and then attach the file there. Because if you just hit reply with your attachment to the mass mailing that goes out to all the class members, that does not always, maybe never delivers. So just I want to make sure I get your, material. I don't want you to miss any of the points that you've earned for that. So just to make sure that we're all clear, make sure that you create an email and then attach the file to that. Hey, Bill. Nice to see you too. Okay, so just reminders about the schedule that we have, that you have your quiz on Thursday, which is on chapter 12. And after that, we just have one more chapter in the book to study. And that's chapter 9, which is all about ethics, morality, and the topic of the moral. So that's going to be our last subject. We're going to cover that next week, Tuesday, Thursday, and then also one additional meeting on it of Tuesday, the 12th of May. And then there's just review for the final. There's also a fourth homework assignment, but I want to wait until you guys take your quiz to assign it to you. So after Thursday, over the weekend, basically, I'll give you guys another Canvas message, which will show you the directions for how to do your fourth homework. It's basically going to be critical analysis of the media, and you're going to be asked to watch a little bit of televised news broadcast and then try to write a short report where you go over some points of critique using concepts that you've learned throughout the class. So more instructions and details to follow on that, but I want to do one thing at a time. So for now, let's focus on this quiz that you'll take Thursday the 30th, next class, 48 hours from now. And then after that, over the weekend, I'll send you your directions for fourth homework. So what's left over after this quiz that you're going to take this week is just the last homework and then the final exam. So we're getting closer to the end. Your last homework that you submitted last week, I'm pretty much done with that. So I was going to send an announcement later tonight telling you guys that you can feel free now to send me any message or email requesting your score on that assignment. And if you want to know your score for anything else or overall, please let me know. Just so you understand, though, it could take me 24 hours or so to give a student a response, just because I have a lot of emails coming in. But once you see my Canvas announcement, I'll post it later today. You can feel free to ask for your grade on the third homework. Most people did pretty well on it as long as they turned it in and made a good faith effort to find the examples. So you shouldn't be too worried about it. But anyway, that's behind us now, and we got a couple things to look forward to. Oh, hey, Veronica, not to worry. Everyone's dealing with computer and Wi-Fi issues, just doing the best we can. But as you guys know, right, these lectures are not only broadcast the one time live. You can always come back to the same channel here and watch them at a later date or time because they're archived. And the dates for each meeting are listed in the title. So anybody who ever has a problem or lost connection or something, just feel free to go back and watch that part or the whole thing again. It's also nice for your review and for your study. You can go back and witness the lectures that you need notes for at your leisure. So anyways, but welcome Veronica and everyone else. All right, so if there's no questions about that stuff, you guys will let me know if you have any questions, but if you don't, then I guess I'll just continue now, talk about the remaining topics of chapter 12. So just so we have the concept in mind, we're talking about chapter 12, all about science. Okay, so I'm just going to tell you about what we covered last time on the topic of science. First of all, we just defined the term. Science is when it's reasoning from observable facts to testable explanations for those facts. So in science, we observe the world, we notice that certain phenomena exist, and then what we try to do is explain the reasons that those things happen or what causes them. And the explanation for the cause is called the hypothesis. That hypothesis is then tested in order to see if it's correct. So at the end of the process, you have a testable explanation for some observed phenomenon. And that's very important because once you understand how phenomena work and what creates certain effects, then you're better prepared to deal with those things and to also perhaps make more efficient the conditions that are necessary for a more productive and happy human life or a happy human society. So science really helps us a lot. It's the basis that we use to produce technology, medicine, and therefore we're all greatly indebted to the work of the field of science. We talked about some important figures in the early history of Western science. We talked about Nicholas Copernicus, who discovered heliocentrism, which is the fact that the sun is at the center of our local cosmos, but not the Earth. The old view, geocentrism, which dominated before him, was stood up by the church because it was considered very important based on church doctrine, to think that the earth was at the center of all things because, of course, the idea is that God created us in his image and he would have wanted mankind to be in a central position. So Copernicus discovered otherwise using telescopes, and so did Galileo, and they were really threatened and pressured by the church and the state at that time to recant their testimonies. But anyway, we all know nowadays that definitively the sun is at the center. So that was an important contribution, and it paved the way for future scientific discoveries that would be considered separate from and distinct from the religious paradigms that existed before. So it created a leverage and space for a whole world of new scientific discoveries to advance, free from the strictures of ecclesiastical authority. And then there was also Sir Francis Bacon, who basically formulated the steps of the scientific method, and we will talk a little bit about the method today, actually, so I'm going to save more of the discussion of that for a moment. But that's a fundamental process of science where you observe things, hypothesize what causes them, and then create an experiment to test the hypothesis. Then we talked about what are some basic assumptions that are built into science. So just a review of those concepts. There's the idea of empiricism, which is the view that most human knowledge comes from observation and from the five senses. So that's a core assumption of science. It's also assumed that the concept of objectivity, that there's a real objective world and universe outside of your mind, and that the belief of science is that we can come to learn about it as it really is, not just as it seems to be or as a person's opinion about it might be, but how it really is objectively, that we can get to objective truth and that we can do so with no bias. Another basic assumption of science, that we can really discover facts, that we can discover objective facts and get to them in a way that is not biased or reflective of prejudice or personal influence toward like cognitive or confirmation bias. Now, there's also the assumption of materialism. This is a word which sometimes philosophers also refer to as physicalism. To be honest with you, I kind of prefer the label physicalism because it does not harbor the false associations with other unrelated meanings of the word materialism. But anyway, in our book, they've chosen the terminology materialism, which means that a person thinks that everything in the universe is just made out of matter. Everything's made out of physical matter, which essentially are atoms at the most minute level. Everything's made out of atoms. And according to materialism, even you and me are made out of atoms. So our consciousness, our thought, our feelings, the psychological aspects of your mental life are really just physical facts having to do with the brain. So that's materialism, another assumption of science. Everything's physical. Another assumption was predictability, that once we've identified a cause-effect relationship in the world, that is something permanent and stable. So like, for example, the belief of predictability would hold that since we know how gravity works when there are forces of gravitational attraction between massive objects, that same phenomena is going to be repeatable on and on perpetually into the future. So like a freestanding object dropped from a certain height is bound to fall, not just today, not just tomorrow, but for the rest of all time. Of course, that's assumed and cannot be definitively known because we don't know, I guess, what's going to happen tomorrow. But at the end of the day, the reliability of the induction that we're using in science gives us a reason to think that these patterns remain stable forever. So cause-effect relationships that we understand will be repeatable and will recur forever throughout space and time. And then there's one more assumption, which is unity, that the universe overall has an underlying unified dynamic structure. So that eventually, anyway, we should be able to discover a single set of scientific laws and principles that could explain the occurrence of all events, from the largest down to the smallest. Then I guess we did talk a little bit about some views about the relationship of science and religion. So just a quick reminder about what we said there. The textbook mentions that there are 4 possible perspectives or attitudes that a person could take towards the relationship of science and religion. On the one hand, someone may take the viewpoint that science should be prioritized over religion in the event of a conflict between them. So that would be the one who says, if they don't agree, I'm going to go with science. Another perspective is the opposite, which says to prioritize religion whenever and if there is a conflict between it and science. So that would be like the basic perspective that if science and religion don't agree, I'm going to go with the religious viewpoint. Then a third view is concepts and subjects. So that's another possibility. A person, for example, could think that science is all about considering causal relationships and physical relationships in nature. And then you could imagine that religion's on a separate topic, which is just the spiritual, the moral. Anyway, that's the third view. And then the fourth view is that they may be actually compatible. So according to a possible interpretation of religious claims, maybe they don't say something that is different from what the scientists' claim is. If they're interpreted in the proper way, maybe they really do reach the same conclusions. So, like, for example, a person might say that in the Bible, when it claims that God created the universe in 7 days, maybe it didn't literally mean like a 24-hour day, and therefore there's no discrepancy between the scientific account of the universe, which says billions of years passed before humans emerged, and the book of Genesis, which says that this was done in a week. So, okay, different views about relationship of science and religion. So that's kind of where we finished, I believe, last time. So now we're going to pick up from there and just kind of go through the rest of the chapter 12. So the next thing in chapter 12 that is mentioned is the scientific method. I want to then talk to you guys about all the steps in the scientific method. First, though, I kind of wanted to refer to something that's also discussed in our book, which is how the scientific method bears some general similarities to the steps in the critical thinking process. Okay, so comparing the critical thinking process to the scientific method. Okay, so maybe you can remember one of our earlier meetings where we talked about the 3 steps of the critical thinking process. So there's blank, blank, and blank. What do you remember about that, if you can? What are those steps? It goes from 1 step to a second to a third. It's a 3-part process that we've discussed way back, but hopefully your memories have not failed you and you can remember that. So what are these steps in the critical thinking process? So it's 1 step that leads to a second step that leads to a third. What are those 3 steps in the critical thinking process? We begin with what? See what you know. There's no diffusion of responsibility. It's your responsibility. So tell me the answer. What are the steps in the critical thinking process? Experience, interpretation, analysis. Good, Carmen. Exactly. That's right. So those are the 3 steps. First of all, the critical thinking process, as you say, begins with experience, moves on to interpretation, and finally reaches the 3rd phase of analysis. Now, the scientific method has some basic commonalities with that, because in the scientific method, okay, so this is a critical thinking process over here. This is the scientific method over here. But the scientific method has similarities because it starts with the concept of observation, okay, which then moves on to hypothesis, and ultimately leads to test or experimentation. So there are these basic similarities in the 2 concepts, because remember that when you critically think, you begin by just having an experience, like something happened, some event occurred either to you or to somebody else, and you just note what the experience was. But you're not yet trying to explain or interpret why. just say, for example, I don't know, I failed my test. That's just what happened. But when you go to the interpretation level, now you're trying to actually give some reasons or explanations why it happened. So if a person failed a test, they might say, explanation, I didn't sleep enough, so that might be the reason. I wasn't able to focus because I was too tired. Analysis is when you go back to the interpretation and you question it again. You say, well, is that really the right interpretation? So maybe the person's first instinct was, I needed more sleep. But then when they reconsider it a little bit, they think, but I've had a lot of other good successful outcomes even when I had less sleep. So maybe it had more to do with my decision previous weekend to go out and hang out with my friends instead of read the book, because I thought that I could just cram it later. So now they're giving you a different analysis, a different interpretation based on the full light of reflection that comes later. Now, that is generally similar to the scientific method, because in the scientific method, there's more than actually 3 steps. The book wants to kind of just give us a sense of how 3 steps in the method can generally be associated with the 3 parts of the critical thinking process. But in the scientific method, the first stage is just observation. You observe something happening in the world which you don't understand why or how it happens yet. You don't understand the cause. So after that, though, you move on from just noting that something happens, like, I don't know, bees are dying off. And then that's just observed. That's just noted. Just like an experience is simply taken in before one tries to explain why. But after you have this observation of some noted fact, you give a hypothesis which tries to give an explanation why. So right now there's a lot of insects that are in global decline. The textbook talks about the conspicuous case of bees, which I guess bee colony collapse disorder is a real thing. Honeybees around the world seem to be going down in overall aggregate numbers. That's something that we observe, but why is it happening? So a hypothesis would try to give some reason, and many different hypotheses are possible. But say that a person thinks, I don't know, it has to do with the development of cell phone towers, and the radiation that's coming from the cell phone towers is threatening the life cycle of the bee. Then one goes on to test. Now, testing is quite similar to the analysis stage of critical thinking, because remember, in analysis, you go back to the interpretation and you ask, is it correct or not? With testing of a hypothesis, it's somewhat similar, because you're trying to question, is this the right hypothesis? The test is supposed to reveal whether it is the right hypothesis or not, because the results of the experiment or test will either confirm or disconfirm that hypothesis. So in the case I mentioned, well, we'll go over it in more depth next, but like, taking the honeybee example, they're dying off. What could be the reason? I don't know. Is it global warming? Is it cell phone tower radiation? Is it some other pathogen that's being produced by, I don't know, newly formed human industries? Take a hypothesis, and then the test would be generated whereby someone kind of tries to recreate conditions which are likely to justify the hypothesis of what the cause of their declining numbers are. And the test is either going to bear out the truth of the hypothesis or it's going to invalidate it. So we basically see a commonality in the 2 procedures. After that, I want to go over the steps in the scientific method with you in more minute detail, because it's a little bit oversimplified to just talk about 3 steps. There's actually at least 5, as our textbook calls it. So steps in the scientific method, that's our next piece of notes now. Okay. Okay, so first of all, the first step, it's called identifying the problem. And what that is all about is that you observe the world and you identify some unexplained phenomenon that's in the world. So So it says there, one observes the world and identifies an unexplained phenomenon. So it could be that you look into the world and you see that there's this global decline in number of bees or other insects. It could be that a person looks at the world and like sees a volcano erupt, and at like one previous point in human history, there's not yet an explanation as to what causes that event to happen. It could be a person looks out into the night sky and sees gathering clouds, and then in the morning there's a thunderstorm, but they don't really understand what is the reason that thunderstorms happen. So as human beings, we're a little different than the other animals. The other animals, they just live and die and eat, mate, sleep. We do those things too, right? But we also have detailed knowledge, scientific knowledge and empirical data that we know about our universe and our world. We know how things work. Like a wild animal seeing a hurricane, volcano, tornado, or anything else that they could possibly observe would never be able to gather even the faintest idea of what the conditions are that produce those outcomes. But as human beings, we're intelligent creatures, and so we want to take the next step to try and understand why things happen so that we can be prepared in the event that they happen again, if there's any necessary preparations that we should make or actions that we should take responsive to them. So without a problem, something to explain, then there's nothing for science to do. So it has to start by just pointing us towards some event, some observed facts that we don't yet understand why they have happened. But we want to understand. And so the second step of the process after that is to develop an initial hypothesis. Okay. Develop an initial hypothesis. So first of all, what is a hypothesis? It is an educated scientific guess to explain an observed problem or phenomenon. So one gives an educated scientific guess to explain the occurrence of the observed problem or phenomenon that we talked about in step 1. Okay, so the word hypothesis is built into the description of this step of the scientific method. A hypothesis is, as you see it, an educated scientific guess to explain an observed problem. So, like going back to the random example of the bees that are going into decline, that's just a problem. That's what's been observed. What could be a hypothesis? It could be, some people said that it seems traceable to the outset of widespread mobile phone, cell phone technology. So some people think, could the radiation emitted by cell phone towers mess up the life cycle of bees? That's one possible hypothesis. I guess another one could be changed weather patterns due to increasing global temperatures brought about by carbon emissions. Maybe that's the reason that they seem to be having troubles and declining in greater numbers. Maybe there is some strange opportunistic virus or bacteria that only affects bees, and that if we did a close enough study, we would be able to identify some evidence of that. So various hypotheses could be given, but what a scientist does is they settle on one that they want to try and test, and they use that as their working hypothesis. So 2 things have been stated in the method so far, starting with just identifying something that you want to explain. That's identifying the problem. Second step, giving your initial attempt anyway to answer the question, why did it happen, or what is causing it? Okay, so then we get to our third step in the process, and due to limitations of space, I just have to keep clearing the board and adding new information. So we've got our first two. Let's move to number 3. So number 3, I kind of thought in a way they're being very precise to try and add this, because in a way you could have maybe skipped over it and we'd still get the big picture. But in the textbook anyway, they added an additional step here, 3, which is to gather additional information and refine the hypothesis if necessary. So that's step 3. Gather additional info and refine the hypothesis. Okay, so sometimes after your initial data collection, after you've made the hypothesis, you might realize that you have to make some slight adjustments or alterations to the hypothesis based on that initial data collection. So that's the idea here. After gathering some initial data, make adjustments to the hypothesis if necessary. Sorry, I didn't mean the word initial. After gathering data, make adjustments to the hypothesis if needed. Okay, so basically sometimes you have your first basic hypothesis set forth, but then you want to maybe make a slight tweak or modification to it because your data collection shows that that needs to be done. So take, for example, the fact that, I don't know, since around the late 90s and all the way up until really just the pandemic, there was like a bunch of mass shootings that would be happening in, public places, schools, and all kinds of stuff. And that was like a big epidemic in our country, and maybe it would be again if we ever return to like full, public-facing activities every day. But the thing is, why does it happen? It's a problem that can be identified. It seems that we have higher rates of those kind of mass shooting events in our country than in other countries. So what could be the reason? Maybe here's a hypothesis that somebody had, which I don't agree with, by the way, but maybe someone thought, oh, could it be because of the exposure to, violent video games? Maybe that's the real reason that people are willing to, commit such atrocities. But then they look at some statistical information and they see no general correlation with all video games, but maybe just specific genres like the first-person shooter games or whatever. So they refine their hypothesis based on the collection of statistical data according to that fact. So they'll say, okay, maybe it has to do with early childhood exposure to certain types of first-person shooter genre games that got refined down from just the bigger concept of like violent media or gaming. Now, look, that's a hypothesis. It's not something that I believe at all personally, because the kind of video games we're talking about exist in all global cultures, and it seems like if that was the right explanation, then that would be confirmed by the greater rates of these events happening in all the different places where games are played like that, like in Asian countries and stuff too. But anyway, I'm not saying I don't agree with that hypothesis, but just for the sake of illustration, that's one case of maybe someone modifying a hypothesis to reflect their initial data collection. Maybe the person who looked at cell phone tower radiation started to examine the rates at which bees are dying in various parts of the world where these towers exist. And they actually start to see that there's no measurable impact except when they look at 5G radiation. I'm not trying to spread that weird conspiracy theory at all, but maybe, for the sake of discussion, somebody thought it seems to be having a bigger impact when we change the bandwidth of the cell phone tower emission. So then they modify the hypothesis to make it a little bit more specific. Okay, so once you've got your nicely narrowed down and tailor-made hypothesis, you're ready to move on to an all-important fourth step, which is to simply test the hypothesis. Okay, so let me put that here. Step 4. test the hypothesis. So what that amounts to is, after doing your observations and collecting the data, now you're ready to test the hypothesis. So either in a real world or laboratory setting, you create an experiment which will either confirm or disconfirm the hypothesis. So either in a real world or laboratory setting, a person conducts an experiment, or you could call it test, to see if the hypothesis is actually correct. Okay, so usually the way a test of the hypothesis works is that you want to have a situation where you can control a variable and then see whether or not the addition of this controlled variable will make a difference as the hypothesis predicts. So for example, let's see if you can make a guess as to how this type of test would go. Suppose that somebody thought bees are dying off. My hypothesis is cell phone tower radiation is causing it. That's their hypothesis. So how do you think a person might try to test that hypothesis? You can't just say, here's what I think, now you go and tell me if it's true. The scientist has to be able to conduct an experiment to reach conclusions. So if the hypothesis is bees are dying because of the exposure to cell phone radiation, how could that be tested, you think? Just, imagine how that could possibly be tested. What would be the method of experiment there? You'd have to, what would be your materials? We could start with that. You'd have to begin by getting what? How could you, okay, so bees exposed versus not exposed, correct. So you'd have to have a control group and another group. One of the groups would be exposed to the dependent variable of this cell phone tower radiation. So you, I guess, would have like a colony of bees in an enclosed space. You'd pump that space full of this supposed radiation, and then you'd have another colony that was not exposed to that condition. And then you would, of course, observe the outcome. If your hypothesis is correct, then what should we see in the group which has been exposed to the radiation? What we should see if the hypothesis is correct is that it having a negative effect on their numbers and their life cycle. Now, if that is seen by means of that exposure to the control group, then that seems to give confirmation to your hypothesis. So you would then just say, okay, I think my hypothesis has been confirmed to some extent. On the other hand, maybe your hypothesis is not confirmed by the experiment. You have the control group of bees, you're exposing them to tons of radiation, but there's no measurable impact that you can see between them and the other group that was completely not radiated. So again, it's not a foregone conclusion that your hypothesis is correct. That's the whole reason that you have to test it. The test can have two possible results. It can confirm or it can disconfirm what your hypothesis was. And so in this case, I'm giving you kind of like a controlled laboratory type of experiment. Sometimes you can also conduct tests or experiments by just evaluating or sampling statistical data that's publicly available. But whatever the method is, some test has to be conducted. That brings us to the fifth and final step. So the final step of the scientific method is to evaluate the hypothesis based on the results of the testing. So step 5. Okay, so after the test, we have some results. And these results either tend to confirm or disconfirm the hypothesis. So, well, we have to now explain what you would do in either of those two cases. If the test confirms the hypothesis, then you can publish the results and forward it to the remaining part of the scientific community so that they can hopefully reproduce and replicate your results for further confirmation. Okay, so evaluate the hypothesis based on test results. If the test confirms your hypothesis, publish the results for further replication, confirmation by other scientists, by the other part of the scientific community. On the other hand, if the test disconfirms your hypothesis, meaning that it did not show that it was the correct hypothesis, let's say D, because that's a D hypothesis, then go back to step. Question, what do you think that should say? Suppose that you did this experiment, this test, and it did not verify the hypothesis that you had. So you can't publish those results because this is not the right hypothesis. But then you have to go back to a certain step. Which step do you think you return to if your hypothesis was disconfirmed by a test? Go back to step, what would be the number? Based on your notes here and your common sense. You would return to which step? No, Veronica, not number 1 actually, because you still have the same problem to explain. So like the bees are still dying off. You're not going to find a different problem. You still have the same problem. No, because you have a failed hypothesis. You can't just keep testing the same failed hypothesis. We're talking about the case of disconfirmation, right? So no, it's not 3 either. So look, take the case of bees. They're dying off. That's the problem. A hypothesis could be that it's about radiation. Suppose that you tested that and you see that that's not the reason. You therefore don't have this hypothesis to work with anymore. So if you go back to step 4, that would just be creating a different test of the same hypothesis. But if it's been disconfirmed, then you're not supposed to keep testing that hypothesis because it's over with. So you go back to step 2, exactly. You have to create a new hypothesis, a different explanation for the observed problem. Because look, you still have to explain that problem. It has not yet been explained by the first attempted hypothesis. The test process has shown that that wasn't correct. So you got to try out a different hypothesis. If it's not the radiation, what could it be? Think of something else and then test that. And you then repeat the steps. So then go back to step 2 and repeat. Then go back to step 2, form a new hypothesis, and do the process again until eventually you're going to get the right fit of hypothesis and experimental confirmation in terms of the results. So maybe I've, let's say, got a dog that I feed food to at night or something, and it's an outdoor dog. And suppose that I'm noticing that the food is all gone in the morning, right? So the dog's hungry, it's not able to eat the food because it's been removed. And so my issue is like, I don't know where the food's been going. This is like a crude scientific problem. It's not like a big world issue, but maybe a person would want to know what's happening to the food. So the thought is, sorry, Veronica, your question here. I was stuck on the idea of refining the hypothesis instead of finding a new one as stated in 2. Well, yeah, I mean, you already refined the hypothesis and you already tested it, but the test shows that it's not correct. So you just have to try and find a different answer to the question, why did this problem happen? Okay, so in my weird case of this dog with the missing food that you left out, you might think, well, is this having to do with animals? Maybe there's like some type of like passing by varmints that are like, you know, coming and taking away the food that I'm leaving for my dog. Maybe there's like some kind of local colony of prairie dogs or something that's coming and looting the food that I'm leaving out for it. So you can easily test that hypothesis by putting a camera out there, right? Suppose that you put a camera out there and you don't see any such animals, but but then you do start to see, like, I don't know, like a gust of wind picking up and taking the food away or whatever, you might have to reject your initial hypothesis, come up with a different one based on that. I mean, that would be easy to test because it's just done by means of a camera that witnesses the observed events that you're hypothesizing about. But in the bigger picture of science, we oftentimes don't have something as crude and straightforward as cameras to detect whether or not the hypothesis given is true or false. But on the model of that thinking, this is basically the method that you employ. You have a problem, you want to try and explain why it happens, what's the cause, right? What's the cause of this thing that I observed? If you don't get it right, what your explanation is on a first attempt after you've tested it, then it's back to the drawing board and trying to create a separate, different explanation of that same phenomena that still has to be explained. And so science continues to work in this way until we get the right explanation. And when we have the right explanation, we'll know it, or at least we'll have a good sense of it, because it's going to be confirmed by the results of an experiment. I don't know, like, let's get pretty high level. Einstein said that if my theory of relativity is correct, then you should be able to see light bent from around the surface of the sun when there's a solar eclipse, because basically the massive surface of the sun is going to warp the light as it bends around it and curves. So we should actually be able to see objects that would normally be occluded by the sun from shining behind it. And he says, if this is seen when we have the next eclipse, then that gives confirmation to my hypothesis. If it's not seen, and that shows that my hypothesis about how light propagates through space is false. And when they did have an eclipse, they saw exactly what was predicted by his hypothesis, so that was confirmed. Now, okay, so we can erase all the stuff about the steps in the scientific method. I wanted to just make one point about the word hypothesis versus the term theory. They're very similar. The only real difference is that a theory is just a very well confirmed, well-established hypothesis. Well-proven, well-confirmed hypothesis is a theory. So you can think of a theory as like a hypothesis graduates to being a theory after it's been reconfirmed over and over and over again by the members of the scientific community. Then it starts to attain the status of theory, which we regard as being the closest approach to the truth that we can have. It's also important for you guys to understand that in science, absolute certainty is never claimed. What is claimed is that we have a very, very well-established theory that's been, confirmed over and over again with no disconfirmation. But science is based on the method of inductive reasoning, which we've learned about. And with induction, there's never an absolute claim of certainty that the inductive conclusion must result. It's simply said that based on all the evidence of our experience and prior data, it's very likely to recur. So scientific hypotheses are couched in the language of induction. They say, well, we have a theory which explains the occurrence of some phenomena, and it has not been invalidated or disconfirmed by any test, but that means that maybe we have like 99.999% certainty in it. But scientists always allow for the possibility that new data from the future will come forward to invalidate an existing theory. Usually, when a theory's been very well proven, it's kind of hard for it to be debunked, but that's not 100% of the time that it can't happen. Even Newton's laws of physics, right, which were considered the standard in science and physics for hundreds of years, were eventually invalidated by the more precise work of Einstein. So it's not impossible for a well-established theory to be replaced by a different one, but it needs overwhelming evidence. And so usually we hold to our theories, but we always keep some small degree of open-mindedness that they could be disconfirmed in the future. Okay, so I've talked to you guys then about the steps of the scientific method. Now I want to tell you guys about how to evaluate scientific hypotheses or theories. So what are the qualities of a good scientific hypothesis? That's what's discussed next. Not all hypotheses or theories are created equally. Some are better than others. And by knowing what the qualities of a good scientific theory are, then you'll be better able to distinguish the good from the bad. Okay, so qualities of a good scientific hypothesis. Okay, qualities of a good scientific hypothesis. First of all, just relevance. Relevance to the problem. So basically, your hypothesis has to at least be related to the topic that you're trying to explain scientifically. So a bad hypothesis can easily be dismissed right away if it bears no relevance to the subject that you're trying to explain. Say, for example, that, like we have a lot more hurricanes now and a more intense hurricane season if you just examine meteorological data over the past 15 years compared to previous decades before that. So, okay, that's an observed problem. What's the reason for the increased intensity and number of hurricanes in a given year as we get closer to the present day? What if somebody's hypothesis is this? Well, okay, I've noticed that over that same time period, the rate of divorce has greatly jumped up. So I'm drawing a connection between these two. They're correlated. There's more hurricanes, also fewer stable marriages, more divorce. Maybe that's the reason. Maybe the hurricanes are happening because more people are getting divorced. But that, of course, cannot be the reason. These are totally separate domains of inquiry. One is a sociological thing. Another is about nature and weather. So there's no possibility that could relate to the question that's being asked, why are the hurricanes happening? So you need to make sure at least that the claimed hypothesis is within the realm of significance or relevance to the problem that you are trying to study or to investigate. Next up, consistency with well-established theories. Consistency with other well-established theories. Okay, so basically, a good hypothesis or a good theory will fit in with and will not contradict other well-established theories. So will fit in with and not contradict other well-proven theories. Okay, so this is all about a concept in science that science is supposed to be one integrated, unified body of knowledge. It's all supposed to fit together. So a new scientific hypothesis that arrives should basically not invalidate or contradict the other well-proven things that have come before. It's not like with each new generation of science, we completely discard everything that we've learned in the past and start fresh. Instead, you got to think of it as like standing on the shoulders of giants. That's what scientists sometimes say they are doing because they're building on the results of previous scientists and researchers. So a good hypothesis should not contradict these other well-established theories. They should fit right into them and build on them instead of undermining them. Say that a person thought that, so they see presents arriving underneath a tree. This is a little kid, perhaps, little junior scientist. They see presents arrive under their Christmas tree around the holidays, and they're wondering how'd they get there because their parents are telling them, I didn't put them there, right? So they are going with the hypothesis that it's Santa that delivered the gifts with his magical sleigh, right? But if that's the hypothesis, that would contradict so many other things that we seem to understand very clearly about laws of physics and aerodynamics. For example, if Santa's the one responsible for the placement of the gifts, if that's the right hypothesis, then he has to be able to commandeer a reindeer-driven sleigh through the air. But since we know from well-established theories that reindeers are terrestrial mammals, and since we know from well-established theories how aerodynamics and it works, therefore there'd be no mechanism of propulsion to keep this thing up there suspended in the air. So we would have to basically reject fundamental laws of physics to sustain this Santa Claus hypothesis. Therefore, it's a bad hypothesis. A good one will not contradict other well-established things that are easily understood and proven already. I don't know. Suppose that somebody thinks that the Earth is flat instead of a sphere. For them to hold that hypothesis, that would contradict everything that we think that we know about the elliptical path that, say, satellites orbit in when they fall in a smooth free fall pattern around the curved globe surface of the Earth. So, I mean, for the flat Earth hypothesis to be sustainable, we would have to completely ditch everything that we think we know about how global circumnavigation of the planet by satellites works. And therefore, it's a bad hypothesis. So a good hypothesis doesn't force us or require us to toss out or throw away major aspects of things that have already been well proven. So that's a red flag of a bad hypothesis, if it's contradictory to other things that have been well proven. But as I've said before, although it's rare, there's a slight possibility that a revolutionary hypothesis can come forward and require us to abandon earlier results that we've learned about. But that takes overwhelming evidence. That's the exception. That's not the rule. Like, for example, Einstein's theory of relativity does invalidate certain elements of the Newtonian physics, but that's kind of an exceptional case. For the most part, scientific understanding builds on what has come before, and at the margins, Newton and Einstein largely agree. There's just a couple of infinitesimal discrepancies when you talk about action at a distance between objects in space and things like that. So, okay, consistency with well-established theories, that's a second hallmark of a good scientific hypothesis. Next up, we're going to talk about simplicity. Okay, so changing my notes here for that. All right, so this is the criteria, the quality of simplicity. I don't know if I was numbering them before, maybe that's not necessary. So another quality of a good scientific hypothesis is this concept of simplicity. It's sometimes also referred to by a second name, Occam's razor. Okay, so the idea here is just this, that if you have two different competing explanations for one phenomenon, the simpler of the two is the one that is likelier to be correct, likelier to be true. So again, the simpler of two explanations by comparison is the one out of those two that's likelier to be the correct explanation. The simpler of two explanations for an event is likelier to be true. That's a basic principle of science. It's sometimes called Occam's razor because that's given from the namesake of a man named William of Occam. That is a medieval philosopher, theologian, and I guess you could say early scientist who posed this concept, and it's been, held on to ever since. So yeah, what it says there, the simpler out of two explanations is likelier to be correct or true. Let me help you understand that maybe by way of an example. So suppose that you parked somewhere, you drove somewhere and you parked. When you come back to where your car was, it's not there anymore. Okay, so that's a problem now. Now you're doing a little scientific reasoning for a moment of a kind. So you might now have hypotheses about what happened to the car. What do you think would be one basic reasonable hypothesis to explain an event like that? You go where your car's parked, now it's not there. What could be the explanation for that? Hypothesis, anybody? What do you think could be, for the sake of discussion? If that happened. Hope it doesn't happen. But if it did, what might be your first initial hypothesis? What do you think? Toad? Okay, Carmen, possible. You could say, maybe I inadvertently parked in a stall that I was not allowed to park in. Maison, you're saying maybe it's Stolen, that's another hypothesis. Those both sound fair. It could be that you didn't properly secure the car, or it got broken into, whatever, jacked. Now, let me give you two hypotheses, and just think about these two for the sake of our little example. Let's just compare these two. Suppose on the one hand, the person's thought process is maybe it was towed. On the other hand, maybe it's not there because it was taken away by the aliens to outer space. Maybe they abducted my car and took it away. Now we have two competing rival hypotheses, the towing hypothesis and the alien abduction hypothesis. But which one of those two could be said to be the simpler hypothesis? What's the simpler one? The one that involves fewer assumptions out of towing versus alien removal. We've got two hypotheses. One of them is simpler, though. Which one in those two? It's a little simpler to just assume that what? That it was towed, right? Exactly, because although the other hypothesis is one possible explanation, I guess, what other stuff do you have to assume for that hypothesis to be true? For it to be true that the aliens took it, you have to assume a whole bunch of added stuff that you don't have to assume for the simple, straightforward thesis that it was towed. In order for it to have been taken by aliens, first of all, you have to assume what things? Like, for example, you have to assume that what? I'm sure you can tell me. Assumptions that have to be given to sustain the more complex hypothesis here. All kinds of things. First of all, you have to assume they exist, right? So you have to assume the existence of extraterrestrial alien life. Then you have to assume that not only there's aliens out there, but that they are so advanced that they've developed means of transport that can carry them to whatever part of the cosmos they're in, to our planet Earth, which, I mean, even the closest star to the planet Earth is over 4 light years away. So that would be a pretty impressive technological feat that human beings can't achieve. So you have to assume not only that life exists, but that it's highly intelligent. Then you'd have to assume that not only does highly intelligent life exist, but that it has a particular interest in your car for whatever random reason. Now, none of those additional assumptions have to be put on the table for a person to just go with the hypothesis that it was towed or maybe stolen. So in competition between those two hypotheses, clearly the simpler one is the winner. It's likelier to be true. I don't know, when you have conspiracy theories, sometimes they violate this principle because they're oftentimes more complicated than the official theory of why things happened. So like, I don't know, for example, the flat Earth hypothesis is way more complex than the sphere hypothesis, because you'd have to then assume that all images ever shown from distant locations like the moon, or from satellites that orbit the Earth, or from space shuttles that we send into space, you have to assume that those are all faked, and that you'd also have to assume that there's some kind of diabolical cabal of people that for some reason in the scientific community want to confuse you about the correct shape of the Earth. It makes no real sense, but those assumptions, right, are needed in order for somebody to really take seriously this flat Earth claim. But you don't have to assume any of those additional things for the globe hypothesis to work. So anyways, the simpler out of two explanations is likelier to be true. It's believed that the universe overall has a kind of parsimony to it. So there's an elegance and a parsimony, meaning that there's a general preference ontologically for the simpler basis of explanation. So yeah, I'm trying to think of other examples that kind of just come to mind. Maybe sometimes when you have a very complex, convoluted explanation for something, but there's a way simpler one that could be provided instead, you should think seriously about whether the more complex one is actually correct. Because look, it's not impossible for it to be correct, but we're talking about what's more probable. And given the general history of science and the success that we've had in approaching things according to these principles, it's usually going to be the simpler explanation that's correct. Okay, so then we've talked about Occam's razor. There's just a few more terms to go over. So next, quality of a good scientific hypothesis is falsifiability. Falsifiability, what that is all about is a good theory is able to somehow be proven false. So a good theory is capable of being proven false. You say your side got blurry and has not cleared. Chris, maybe if you want at any point and you can't read something that's on this board, do let me know and then I can type it in the chat bar. But once it's been erased and I'm moving on, it's kind of hard to know exactly what you're referring to. But yeah, you can always watch it again a second time. And all these topics are in the book too. So there's the book to use as a resource as well. Okay, so falsifiability. A good theory is capable of being proven false. So falsifiability falsifiability is when a theory or hypothesis is able to somehow be proven false. Now, this is a little tricky because I don't want you to get it confused. It doesn't mean that it is false. It doesn't mean that it has been proven false. It just means that we know there's a method by which it could hypothetically be proven false under certain conditions. Now, if there's no way to know what would disconfirm the hypothesis, then there's also no way to test it. In order to test a hypothesis, you have to know what a falsification of the hypothesis would look like so that you can compare successful confirmation against disconfirmation. For example, in the case of my earlier mentioned example of the bees that are dying off in great numbers, the hypothesis that it's due to cell phone tower radiation, that is falsifiable because in an experiment which exposes a sample group to that type of radiation, if we don't see any change in their numbers, then that disconfirms that hypothesis. So that's the only way we can test it, you understand? We couldn't really perform a test of a hypothesis if there's no way at all to determine whether it would be false or not. So in order for a theory to be a scientific theory, it has to have some way of being tested. If you can't test it, then it's not science. But in order to test questions about a hypothesis, we have to be able to know what would count as disconfirmation of the hypothesis. So it's a bad scientific theory when it's not falsifiable. That's the hallmark of a pseudoscientific claim. For example, take the silly horoscopes, right? There's no method that could possibly be given to falsify the astrological prediction of the horoscope. Because say that, for example, you read the horoscope and it said, you're going to get a special visitor this week. And you're like, well, I'm on quarantine and nobody came over at all. The astrologist would just say, oh, that's not really disconfirmation. Maybe you just didn't pay close enough attention to the events happening around you. Did you notice that little bird that perched on your window? Maybe that's what it meant. So what you're going to be told by the defender of all that pseudoscience is that there's really nothing you can do to disconfirm these theories. If you interpret it as disconfirmation, they'll just say, well, we'll put a different spin on what the thing claimed or on what the evidence you had access to was. But if there's no way to disconfirm it, then it's not being tested scientifically, and it's also not being confirmed either. Sometimes people criticize the old psychoanalytic theories of Sigmund Freud because of this. Now, Freud, he's widely known as one of the fathers of psychoanalysis and psychology, and he had some important contributions, like just the general idea of the subconscious. But he also had a lot of weird stuff in there that probably was just a product of a lot of drug use and, superstition and everything else. So he had these ideas of like latent sexual attraction that little children have to their opposite sex parents. So he talked about little boys have this kind of suppressed latent sexual attraction to the mother. That's the Oedipus complex. Little girls, same with the father. That's the Electra complex or penis envy and all that stuff. Now, subsequent generations of scientists and psychologists have pretty much rejected a lot of that because it's not testable. And here's the reason. Suppose that you say to a Freudian, that's false. No way. I don't have any sexual attraction to my mother or father, depending on your gender. So that's a false claim of his work. The Freudian would just say, well, that's all you're saying because you've repressed it into your subconscious. So of course you're not going to be aware of it. You've hidden these self-awareness of these desires, buried them deep in your subconscious. So now nothing counts as falsification. Therefore, there's no way to test it either. So we know that in science, you have to be able to provide a test. If it can't be falsified, then it can't be tested, and so it's unscientific. At one point in history, everyone thought that all the swans were white because all the swans that had been seen to that point were white. But is the thesis or hypothesis that all swans are white falsifiable? Yes, in case you find a black swan or something. And eventually they did discover those, and so that, for example, was falsified. Now, a good hypothesis, you hope that it's never going to be falsified, but you want it to be able to be in principle. And again, that just requires that you have an understanding of what would have to happen for it to be disconfirmed. Let me just read from the book on that. So, a hypothesis or explanation should be presented in a form that is testable and can be replicated by other scientists. In addition to being testable, an explanation must be able to be falsified. For example, the hypothesis that all swans are white was based on observations of hundreds of thousands of swans, every one of which was white. However, the hypothesis was falsifiable since it would take only one non-white swan to prove it false. On the other hand, theories that are able to accommodate all challenges have a critical weakness because they cannot be tested for falsity. For example, Sigmund Freud's theories about the Oedipus complex fail the falsifiability criteria, since if a man claims that he does not have the complex, Freudians argue that he has repressed it into his unconscious. However, unconscious thoughts by their very nature cannot be tested, so there's no way of falsifying Freud's theory. And you know, if you think about, for example, the work of Einstein, he said that you know, if you have two different clocks, one in a state of rest and one that's being accelerated very quickly, then they should actually start to have a discrepancy in the measured time according to the theory of relativity. So test this, and if you don't see a discrepancy in the measurement of the two clocks, then that means my theory is false. But when they did test this, they saw the discrepancy in the time measurements, so it wasn't falsified, but it could have been, and if it had been, then that would have invalidated his theory. Veronica, your question, what page is that? It's on page, well, I'm using the 4th edition text, and so if you have the same one, the 4th edition, this cover, then it's on page 375. Okay. So one more quality of a good scientific hypothesis, and that is predictive power. Okay, so predictive power. A good theory it can be used to accurately predict the occurrence of future events. So future events of the kind predicted by the theory. So you know you have a pretty good scientific hypothesis or theory when it can be used to make correct predictions that end up coming true of future events. Let me give you a few examples like that. Take meteorology, the science of weather. You know, we follow the weatherman report, and it's generally reliable. Now, is there ever a case of a mistaken weather report? Sure. But the general outcome is that what they predict in terms of weather turns out to be the case. So when they say, you know, there's a 90% chance of rain on Saturday and they're telling you that on Wednesday, you know, if you bring your umbrella out on Saturday, you probably did a good thing because it's probably going to rain. And when that rain happens, doesn't that tend to give credibility to the whole scientific field of meteorology? Because if this was just people making up random claims with no real scientific backing or credibility, then the claims would not usually come out to be true. So when a predicted outcome by a scientific field turns out to then happen, that just adds more to the level of confidence that you should have in that type of scientific domain of explanation. Let's see. So we talked about meteorology. How about eclipses, right? So is everybody surprised when an eclipse happens and the sun is blocked out for a little while? Not really, not anymore anyway, because we have astronomers who are watching the night sky and who have detailed understanding of the principles according to which objects pass by in the celestial orbit of space. So they'll tell you even years in advance on the specific date and time that we'll have a lunar or solar eclipse. They can even tell you what part of the surface of the planet Earth that you should be standing on for ideal viewing conditions. And then when that happens, at the exact date and time predicted by the theory, doesn't that make you think that these theories are credible and that they're not just random or baseless? Because if they were, again, then they would not likely get the predictions correct. So science allows us to make reasonable and realistic and accurate predictions of future events, or at least to the extent that a theory does. That's a better theory. Okay, and then so last thing, at the tail end of chapter 12, they talk about science but versus pseudoscience. So just a couple of words about the topic or the word pseudoscience. So the word pseudo means false. So literally, I mean, the meaning of this term is like fake science. But the definition, a little more thorough definition given in the book, is that this is something like a body of explanations that masquerades as science. So that's how they define it there. A body of explanations that masquerades as science. Okay, so the word masquerade is a kind of, I guess, colorful choice of vocabulary for our book, but what is it to masquerade? It's basically, in real life, it's to put on a mask, like a cosplay type thing. So what this is meaning by means of that, I guess, metaphor is pseudoscience is something that wants to look like science. It wants to be presented in a way that seems to have some type of scientific basis or merit. But it's really just like a wolf in sheep's clothing. It's putting on the outward appearance of a scientific field of study, but it's actually not. It's fake science. So a body of explanations that, in an attempt to look scientific, puts on that outward appearance of scientific reasoning, but it's not scientific. And what could be examples of pseudoscientific fields of investigation? So things like, I don't know, astrology, tarot cards, crystal ball gazing, numerology, like prophetic mind readers, or the prophetic writings of Nostradamus. These are all pseudoscientific, and they can be easily seen as such for a couple of reasons. First of all, any predictions that are issued from any of those pseudoscientific realms are going to be stated in vague and unclear language, meaning that anything could be judged as confirmation for them, and nothing can be given as disconfirmation for them. I challenge you, if you want sometime, to block out the names of the astrological signs and then just look at a generic readout of, let's say, a daily set of horoscopes and try and define which one of them corresponds to you. It'd be very hard for you to do that unless there's identifying information given away in the chart itself, because they're written in such a way that almost anyone's experience could be associated with some element of what they say. And that's kind of seen also in other pseudoscientific descriptions of the future. Like if you read the works of Nostradamus, like, so some people are credulous enough and gullible enough to think that those are real prophetic predictions. In some cases, they said Nostradamus predicted big world events in history, like 9/11. But if you read the actual writing that is claimed as this prediction, it's so vague it could mean almost anything. Like it says, "Fire of the center of the earth shall make an earthquake of the new city. Two great rocks shall one time war against each other, and after that shall color red the fresh water." I mean, come on, that could be claimed as linked to any event in world history that has something to do with blood, something to do with rocks, and something to do with a city. But it's just impossible for you to say with any credibility that that is a definitive prediction here of something that ended up happening later. So people are sometimes given it to pseudoscience because I guess it feeds into a feeling of like the occult or the mysteriousness of the world, something that escapes the rational methods of the typical scientific practitioner. But, it's to your disadvantage to believe in pseudoscience, because if you're a superstitious kind of person like that, you can easily be manipulated, exploited, deprived of your wealth. You're going to go and pay people behind a paywall to look at these predictions. You're going to, buy crystals or other new agey, consumer goods on the false pretense that this is going to make a difference for your life in a positive way. Sometimes people like the awe and the mystery of things that they can't fully well justify scientifically. But in a critical thinking class, there's no room for that. So you're going to have to deal with other people or other teachers if that's the kind of thing that you think is valid or reasonable. But it's not. It's my duty to teach you otherwise. So as it says here in the book, pseudoscience is a body of explanations that in an attempt to gain legitimacy masquerades as science. However, unlike science, in which explanations are based on the scientific method, including observation, reason, and testing, pseudoscience is based on emotional appeal, superstition, and rhetoric. Yeah, for example, you can't test. You can't, astrologers, they don't say, here's an experiment which proves that our field is correct. No new tests, no new observational data is ever recorded to give a sense of credibility. It's just supposed to be taken as a given. Astrology, psychic healing, numerology, tarot card readings, mind reading, all examples of pseudoscience. While scientific explanations and hypotheses use precise wording, those of pseudoscience are usually framed in such ambiguous language that it's impossible to determine what would count as verification. Astrological descriptions, for example, are usually so vague they apply to anyone. Because of this, pseudoscientific claims are not falsifiable. For the most part, no tests or experiments are carried out to check the validity of pseudoscientific claims. The few studies that are carried out, such as those on ghosts, are generally poorly designed and rarely replicable. Pseudoscience may also explain the failure of its explanations to stand up to scientific scrutiny by blaming the subject. For example, if you don't find yourself healed by a faith healer, they'll say you just didn't have enough faith. Or if you didn't feel the cold chill of wind when the ghost hunter busts out their little measurement device, then it's maybe because the ghost didn't choose to reveal themselves to a non-believer in ghosts. Pseudoscientific explanations also fail to meet the criteria of predictability. Most are so broadly worded that just about anything would bear out their predictions. Not surprisingly, most pseudoscientific predictions are done after the fact. So it's only after 9/11 that someone tries to say, hey, look at these old writings of Nostradamus, maybe these were predictive of that. But it wasn't like in the year 1970, people were saying, hey, watch out. In 31 years, according to this prediction, this specific date and time, this event will happen. So once again, it's kind of like post hoc. You're just trying to associate the correct prediction with the observed facts after the facts happen. Despite its lack of scientific legitimacy, belief in pseudoscience is widespread. Pseudoscience means fake science. To avoid falling for the empty promises of pseudoscience, we need to know how to critically evaluate claims using the criteria that we have discussed. We should also be aware of how cognitive and social errors can distort our thinking and make us more susceptible to the allure of pseudoscience. Okay, so people out there peddling pseudoscience basically want to just rip you off and make money off of you. It'd be better for you to think critically and see through it. But that's about it. So I've given you guys all the notes for chapter 12 now. So like I've said, at the next class meeting, Thursday the 30th, it's a quiz day, and it's all just on this chapter 12 material. So by studying the book, looking at the notes, looking at the vocabulary items that we've all covered, and watching this live stream or the replay, or both, you should be in decent shape for that. So make sure to be ready to take this quiz through your email on Thursday morning, and I'll be seeing you guys then at the next live stream after that, a week from today. And then we'll start on chapter 9, the last chapter before we start to wrap up the class. All right, everybody, sounds good. So take care, everyone. Have a great day. Thank you so much for being here, and I'll see you back in a week, and you'll take your quiz on Thursday. And I'm finished with the last assignment as of tonight, so people, you can email me for your score on that anytime, pretty much starting tomorrow morning, because I'm teaching throughout today, and then I'll be looking at all my emails in the morning, so I'll check them then. All right, great, guys. Thanks again. Have a good one. See you then.